Hello. Moving further on our universe story was that universe 13.8 billion years ago was so tiny that we couldn't even see it under a microscope. And imagine with today's universe, immensely big that we can't even imagine and can't even see or observe. And a fundamental principle that we intuitively observe in our life: as we expand things, they become cooled down, and as we pressurize them, they become hot. What happens on the background? Children can ask why. Why is that the small particles inside, which call atoms and molecules, they are always colliding each other, and in that collision is what we have named it as a temperature. Yeah, that's the reason why if we go up on the mountains, it's cooler, because the air is not that dense over there. So molecules are less colliding, the temperature comes down, right? Another way of looking at it, the temperature is that these are waves, radiation waves. And if there are more waves, as the temperature is up, there are more waves in the same time. And in other words, the frequency of waves increases with temperature increases, the frequency of that waves that which are coming out increases. So what state we exist now, this is our today's question. What's that temperature has a bearing on whether we are in the liquid form, solid form, or a gas form. And what's the overall situation, how universe looks like now. Today we will discuss that. And let's move. And that is interesting that at the beginning, obviously the temperature was so high that if we look at in the terms of waves, temperature is increasing, then the wave frequency is increasing, and if we keep it increasing, the waves start coming closer and closer and closer, or wavelength starts becoming less and less and less and less. Eventually a stage will come where waves will collapse. There, our today's physics and mathematics works only to an extent, and we don't know what happens. The maximum temperature that we our mathematics and physics works is at one with 32 zeros, that is 140 million trillion Kelvin, right? And you have noticed that we have started our journey not from the 0 second, we have started from 1 over 1 with 43 seconds of a slice. That is, we have done 10 million trillion slices of a second, and from the first slice, because less than that, our mathematics and our physics doesn't work. We don't know at that high a temperature the pattern that we have observed of these forces and particles, three forces and particles. We don't know what their behavior is, and if we really know that, and that means we will be coming closer to a unified theory where we will say it's we can all describe them under one model. So anyway, that's how the very simple explanation as a layman, as we want to equip our school teachers are. And it started cooling down, and imagine at 100 second it cooled down to immensely low, which was compared with the original 1 billion Kelvin, right? And just to make sense of it, because these numbers do not give us that sense of magnitude really in our minds. I have made the sun is obviously pretty hot. Sun is 150 million kilometers away from us, and imagine we standing outside in a desert and at noon, how hot we feel. And 150 million kilometers is not a small distance. 150 million kilometers would mean if we travel at 1,000 kilometers at normal aeroplane or jet cruises, it would take us 150,000 uh, hours, which becomes to 6,200 plus days, which comes to 17 years. So if we go on an aeroplane, if it can't go in the space, it will take more than 17 years to reach the sun, and the sun is very hot. Sun's temperature is on the core 15 million, but on the surface it is 6,000. Our Earth's temperature at the core is 6,000. Obviously, we came out of the sun and cooled down, but that's also a question: why we cool down, why sun is still hot. Keep making these questions. These are all we have to answer, and so 1 billion we can imagine is a too big a scale. At 100 second we were there, but where are we now? We are now at a very, very, very low temperature if it is equally distributed. The scientists have miraculously done some estimation on that. That is almost 0 degree Kelvin. Almost everything should freeze. That's the situation now after 13.8 billion years. And obviously, the question comes to mind: what would happen next? But that question we would leave a little bit wide. And as we know that we now are at a stage where only 4% is that matter of energy which our physics is about, and we have not any clue what the rest 96% of the universe is, except that we have said it's dark energy and dark matter. Dark means we don't know about it. Dark doesn't mean its color is black, right? And one milestone, a big milestone, was when the matter, now we are on the matter, at 380,000 years, we discussed yesterday, the first atom was born, because a universe has to cool down to a stage that they could at least coalesce and combine with each other. Initial stage of the universe, obviously there was no matter, but our estimate is that dark matter was predominant. And at this milestone, 380,000 years we are talking about, when the first atom was born, the ratio was looked like 12% was matter and energy, and the dark matter was more. And this is the ratio. What we have now is only 4%. By ratio, it has decreased. And universe is almost empty. It is almost a vacuum. Imagine the density is only less than 6 protons worth of thing in one cubic meter. So meter is a too big a scale, and protons are at a one over. If we make about 10 billion slices, becomes a 1 angstrom. So 6 protons per meter cube is an almost an empty. And but this ratio, dark matter dark energy, is what kind of determines how universe expands. And this milestone, 380,000 years, where atom was born, was the first time that universe looked transparent, and the temperature was 3,000 degree Kelvin. Obviously, our next question is, in what state we exist now? Are we solid, liquid, gas? Overall, what's the composition looks like? And now our composition looks strange, but we first have to a little bit know that these states of the matter depends on the energy of the particles inside, which is the temperature, as we said. If the energy is huge and they are all in the ionic form, and that's what we call plasma, the sun is in a plasma state. And if we cool down, then it becomes gas, and further cool down, it becomes liquid, further cool down, it becomes solid. And if we cool down at a very, very, very low temperature, then even those spins and those vibrations of the subparticles also stop, and we atoms don't form in that particular way. We call them superatom and sort of stuff, and they are superconductors and superfluids, and their behavior is totally then different. Bose-Einstein condensate was named 1995, and 2004 another form, which is a form of that as well, fermionic condensate. Those atoms are a cluster of that kind of an atoms, are totally different than the normal matter. So when we were in the school, obviously we used to think that it's all gas, solid, and liquid. But we are outliers, exceptions. This universe, our part of the where we are living, Earth universe is 99.9% in the plasma state, the matter part of it, the 4% matter energy that we were talking about. And in the first about 400 million years, the galaxies and these structures were not born. Still things were very hot, and then they start coalescing and the galaxies formed. And there was only actually one matter, hydrogen, and hydrogen started combining into helium. And still 99.97% of that matter part of the universe is still hydrogen and helium. So the upper bigger matters that we are formed of, the carbon, hydrogen, nitrogen, oxygen, potassium, they are in the entire universe, their proportion is 0.03%. So that's how it is. We are not the norm, we are the exceptions and the outliers in the overall, statistically, in the scheme of the things. Now we understand. Next time we will, while come down to zoom into where is our galaxy, how big it is, and in that which part really our sun is moving with its family, and how it moves, in fact, and then come down to our earth, and then those three forces, we will take one of them and start our journey. Thank you very much.